The next presentation is going to be given by Susheel Kolwalkar, and he is going to be talking about the Leatherman terminal project in North Charleston, South Carolina. Susheel, the floor is yours.
Okay, thank you, Gerald. Do I have the control? Okay. Hello, everyone. This is Susheel Kolwalkar, and I work as a senior engineer with Inside Group, and we are a company based in Charleston, South Carolina. And the topic of today's presentation is value engineered foundations supporting buildings and canopies at the UK Leatherman terminal project in North Charleston, South Carolina. And this presentation will address the following aspects of the project. We'll begin by stating some facts about the Port Authority. Then we move on to the details on the project location and site conditions, followed by foundation type and pile driving equipment details. We talk a little bit about the test pile program, and then we get to the design revision, which was the alternative design method that was recommended, which was a neutral plane method. And then just to give you a representative analysis for a building on the project, we'll present some results and then discuss and conclude. So the UK Leatherman terminal, also referred to as the HLT terminal, is a new state-of-the-art 3-berth container terminal developed by the South Carolina Port Authority and is the nation's first new container terminal constructed since 2009. Other relevant stats are that Charleston was the 8th busiest port in the US in the year 2017, and it recorded a record container volume in the following year, which was 2018. Also, the Port Authority facilities drive around $53 billion in annual statewide revenue, and 1 in every 11 South Carolina jobs is attributed to the port. These facts serve as a testament to the port's significant impact on the state's economy. And the project site is located alongside the Cooper River at the southern end of the old Navy base in North Charleston. And the HLT terminal spans over about 280 acres of upland development, which is a pretty sizable footprint. And you can also see here the south side of the property. We've got the Shipyard Creek, and on the north side, we've got the Federal Training Center, also called the Flex C. And this is a more recent aerial view of the project site. So if you drive down to Charleston, you will you'll be driving on the I-26 interstate, and then you can see that these access roads that connect the I-26 interstate with the HLT port terminal. And the port divided this project into 3 phases. The first phase, which you see on the right top corner of the slide, it covered just minimum gated complex with some container yard development and 1 berth, whereas the bottom slide, or the bottom part of the slide, shows you phase 2, where we have an expanded gated complex and a container yard with 2 berths. And the phase 1 is scheduled to open, or was scheduled to open in mid-2021. Accordingly, the first container arrived on March 30, which was last Tuesday. So I guess the project is on schedule. And in order to go over the history of this site, uh, here are some aerial photos. In the middle is a 1939 aerial where we see an old Navy runway right here, which cuts through the marsh. Around the runway, you see some old estuaries and marshlands from the Shipyard Creek. And on the right, you see a 2007 aerial, and the port transformed this area into a dredge spoil. So where basically any scoop material coming out of the Cooper River was deposited here. So all in all, we were dealing with very, very compressive upper soils for this project. And obviously, a lot of geotechnical investigation has been performed on this project. And here we see isopacks or elevation plots of the Cooper Marl Formation, which is the typical bearing layer in the Charleston area. One thing that presented a great challenge is that this marl, which is relatively flat in the Charleston area, has some pretty deep holes in it, meaning that the marl, which started anywhere around, let's say, 40 to 45 feet in this area, it plunged to almost 100 feet to these, bluer zones. And that difference was typically filled with very compressive soft clay. Hence, there's a differential condition across a lot of the site that we had to deal with. And so with the soft soils, the marsh soils, the old dredge spoils, settlement was certainly a consideration. And due to the presence of challenging subsurface conditions, the site was surcharged with about 8 feet to 20 feet of crushed stone for over a year, almost like 14 months, and amounting to approximately 4.5 million metric ton of rock being imported from Newfoundland by ship. And in order to speed up this ground improvement process, weak drains were used in conjunction with the surcharge, which allowed the clay layers to compress a bit faster. And as a part of the surcharge program, geotechnical instrumentation such as settlement plates, piezometers, and extensometers were installed through the site. And the data was used to then create a pretty extensive settlement model, which helped in, number one, predicting when to release the surcharge, and number two, in estimating the expected total settlement over the life of the facility after the surcharge has been released. And during the surcharge phase, settlements ranging from like 2 to 3 feet in some areas to somewhere around 6 to 7 feet in others was measured on the site. And using the settlement model, a post-construction settlement ranging from approximately 6 inches to 12 inches over the life of the structure was predicted. And to talk a little bit about the type of pile foundation and the pile driving equipment that was chosen for this job. And we are specifically talking about the 12 buildings and canopy structures that were built on this facility. And the foundation element that was chosen was a 14-inch square pre-stressed concrete driven pile. And the estimated lengths of these piles range from somewhere around 75 feet to around 120 feet. And the test pile lengths were typically 10 feet longer than these lengths. So some of the piles that we drove on this site were as long as 130 feet. And this qualified them to be the longest ever driven piles for the 14-inch size installed in this low country area. And some of the relevant pile properties that were provided to us are shown in that table. So for example, the concrete strength was around 6,000 psi. The effective pre-stress was 1 ksi, and using those values, the allowable driving stresses were about, the compressive stress was about 4 ksi, and the allowable tensile stress was around 1.2 ksi. Now, these buildings, these piles supporting these buildings had required driving resistances ranging from about 200 kips to 500 kips. And due to this site variability and the range of driving resistances, it presented a little bit of a challenge during hammer selection process. And after running multiple weep analyses for 5 different proposed hammer types, a Vulcan 510 air hammer with a rated energy of 50,000 foot-pounds was selected for pile installation. The hammer is equipped with a variable stroke option ranging from 1 foot to 5 feet. And this helped in regulating the hammer energy such that we did not overstress the pile during initial drive. And at the same time, we could mobilize or prove the pile capacities during a restrike test event. And due to the site variability and the geotechnical challenges, project specifications required that a high strain dynamic testing program be performed. And accordingly, about 40 pre-production piles were tested both during initial drive and during a 14-day restrike event. And this chart shows like a building-wise distribution of the number of test piles, the estimated pile tip elevations, and their corresponding lengths. So for example, building U, there were 4 test piles, and each test pile was about 127 foot long. Okay. And during the course of the test pile program, there were a few constructability issues. The main reason for the issues was the extremely long test pile lengths, and along with that, there was a limit on the lead length of the driving equipment which was there on the site. And this lead length was around 80 to 90 feet, and the test pile lengths were, as you can see, were anywhere between 100 to 130 feet. And that's why the driving setup required pre-augured holes. And the assumption, by pre-augering, by doing the pre-augering, was that the piles would slide easily into the holes, maybe 30, 40 feet, and then that way the hammer can sit on top of the pile and then drive the pile. But what happened was the stone fill, which was there as a surcharge layer, we would often collapse into the hole, creating difficulties for the for the pile to slide, and there was no way for the hammer to get on top of the pile to drive it. So there were a lot of discussions, after this fact to deal with this constructability issue, and hence the need for a pile length reduction was brought up. And that, I don't know why I get stuck, but hold on. But that brings me to the crux of this presentation. And before I get into the neutral plane method, which is an alternative method to design for down drag forces acting on the pile, we will first explain the down drag process in general. So most of the time when we talk about down drag, we mean that the pile is fixed in the ground on some rigid layer below the ground surface. And some of the upper soils will settle or compress. Now we have a situation where the soils are sliding down along the pile and essentially dragging the pile downward imparting some downward force on the pile due to that settlement zone, which is called the down drag force. And the traditional down drag approach, or the traditional design, treats the drag load as an additional structural load that must be supported. And on a site like this, where we have very thick layers of compressible soils, like in the range of 30 to 50 feet, the traditional method of design called for some extremely long piles. So Inside Group, in coordination with the South Carolina Port Authority, recommended an alternative design approach, also referred to as the neutral plane method. And the neutral plane method considers a drag force as a settlement consideration in the geotechnical service limit state and as a structural consideration in the pile element strength limit state. So what this means is, from a structural consideration, we apply the load factors on the drag load and the structural load, and we take a combined load and we make sure that that load is less than the structural capacity of the pile. However, from a geotechnical standpoint, we only use a drag force to compute the settlement in those piles, and that's why it only considers the service limit state. Okay, and we'll get into more of this detail in the next few slides. And there are some great documents out there. Siegel has been talking about it and researching this approach for quite some time. But the NHI document, FHW NHI document 1609, from a practical standpoint, is a better document because it gives a step-by-step approach which can be helpful for us practicing engineers. And this is the slide that shows the step-by-step process. And let me go over that process real quick. So step one is, we know that the ground is going to settle. So that's the first thing. Then, using a traditional pile analysis, we determine that the nominal shaft, nominal shaft resistance of the pile, and the mobilized toe and the mobilized total resistance of the piles. Then we select, the step three is we select the pile toe elevation. And this is a iterative process, like you'll see in the next few minutes. So the step four is we develop the actual load and resistance chart. And the way we do it is, first we plot this dark or the bold curve. We start with the permanent load at the top, and then we keep adding the cumulative shaft resistance, starting from 0 at the top and all the way to the bottom of the pile length. And that's the curve that goes from the left to the right of that graph. And then after that, we use that total mobilized resistance, and we start from the top, and then we plot the dotted line by subtracting the cumulative shaft resistance from each of those increment of depth, and draw this other line. So it's basically an opposite, the same line drawn in a opposite direction. And where these curves cross each other is at magical plane, which is called the neutral plane. And just to understand what the neutral plane is, it's a point where you flip from a down drag condition to a positive resistance situation. So we are at step 5, where we've found the neutral plane, and from the neutral plane we can compute the drag force by subtracting the permanent load from the maximum axial compression force. And yeah, we have the drag force, we have the neutral plane, and then we check the strength limit state. Like I discussed before, we apply a load factor over the drag force and the permanent load, and we make sure that that load is less than the structural capacity of the pile. And if it's not, we go back and we increase the pile length and keep doing the iterative process. And if it's satisfactory, we go to the next step, where we calculate the settlement due to that down drag by by using this drag force only at the neutral plane. And I'll explain that process in the next slide. But if it's within that allowable limit, then we accept the pile. If not, we repeat the iterative process by increase the pile length. So that's the flow chart of this process in general. And just to give you an example of this analysis, we have chosen building E and present the PDA testing and the neutral plane analysis results for this particular building. This is a container repair facility, the one-story tall facility with a canopy, and there were 3 test piles that were driven or tested on this for this building. 2 of the piles were 120-foot long, and the 3rd pile was 91-foot long. And what you see here are the restrike capacities that were obtained as a result of the PDA testing. And then we plotted the neutral plane analysis to those restrike capacities. So the dotted lines that you see here on the left side, going from left to the right, are those plots for the restrike capacities. So the load plot starting from the permanent load or the structural load, which is around 175 kips. And then we added the cumulative shaft resistances for the 3 piles. So these are the 2 long piles, and then the 3rd pile is right here, which kind of agrees with the design load curve that we had. And then we plotted the other curve, which was the mobilized resistance curve, the dotted line going from the right to the left. And this, we used the shorter pile, the 91-foot pile, because, like I said, it agreed well with the design. So we went with that particular pile for getting this curve. And hence we found our neutral plane. And it so happened that the drag force was 171 kips based on the calculation shown. I explained a couple slides earlier, the compressive load minus the permanent load. We got the drag force, and we figured out that the pile length or the pile tip was around -78 for this analysis. And for this particular project, we tried to keep the neutral plane below the marl surface for 2 reasons. One is because the marl is relatively incompressible, and 2, if the neutral plane were to drift up into these softer soils, then it would be a drastically increase in the settlement potential of the piles, and which we wanted to limit. So with that, what we did is we used that drag force. So the first step we did was we checked on the structural capacity, and then after the structural calculations were done, from a geotechnical consideration, we used a drag force and we multiplied that drag force by the number of piles for the building, which gave us a total drag force. And then that force we distributed on an equivalent footing of the size of the footprint of the building. And then we analyzed that equivalent footing at the neutral plane. And some of the input parameters that were used for the settlement analysis were actually back calculated from the surcharge program that we had performed a long time ago on this project. So that gave us a very refined approach of coming with the final settlement, which was around 0.6 inches for this building. And it was deemed by the structural folks that this settlement was satisfactory, and hence we recommended a production pile tip elevation of -78 feet, based on that design. And based on PDA testing, we also said that the hammer has to be operated on a 3-foot stroke with a 13-inch plywood cushion, just to make sure that we don't overstress the pile during initial drive. So using the neutral plane analysis and in conjunction with the high strain dynamic testing on this side, we were able to reduce the pile lengths by around 6 feet to all the way to 27 feet per pile. And there were certain structures like building C, building I think S, and building T, where we don't realize this length reduction. And this was because these were already in production by the time this new design approach was accepted. But even then, we realized a total pile reduction of around 8,000 feet on this project, and which amounted to a total savings in terms of around $500,000, and which was a good saving for the port. And not only that, but pile length reductions also resolved constructability issues on the project, like I explained before. And we could use the same hammer with the same set of leads and still be able to drive all the piles on the project. So with that, I come to the end of my presentation. I do want to mention Ryan Kuiper, who was the lead design engineer for Inside Group. And basically, I manage the dynamic testing side of the project. And I'd also like to thank DFI, especially Mr. Gerald Verbeek and Van Komurka, for allowing me to present about this wonderful project in Charleston. So thank you.